I've been trying to think of a better way to explain why LLMs feel bigger than chatbots. The mental model I keep coming back to is transforms. Not because an LLM is literally a Fourier transform for language, it's not that clean. It is trained, approximate, and lossy, but it belongs in the same broad category of idea. You take a representation, you move it into another space, you do useful computation there, and you transform it back out. That pattern has changed the technology tree before. Fourier transforms let us work with signals as frequencies. Laplace transforms let engineers reason about dynamics, stability, and control systems with algebra. The discrete cosine transform let image and video systems throw away information in ways human perception can often tolerate. Radio, wireless communication, image compression, audio processing, control systems, robotics, aircraft stability, rockets landing on their tails, video streaming over the internet. A lot of the modern world comes from taking one representation, moving it into another space, doing useful work there, and transforming it back. My hypothesis is that large language models are the beginning of another transform like that. Not the same kind, not as exact, not as mathematical, but probably just as important in the branches of the technology tree it opens. Here is the pattern. You start with some representation of the world, a signal over time, a differential equation, an image, a block of pixels. In its original form, the problem may be messy. You can still work with it, but some operations are difficult. Then you transform it. The time signal becomes frequency components. The differential equation becomes something closer to algebra. The image becomes a stack of frequency-like patterns. And once it's in that transformed space, different operations become possible. You can filter noise, you can design a controller, you can compress an image, you can reason about stability. Then, usually, you transform the result back out into the world. Representation in, transform space, computation, representation out. That is one of the deep patterns of engineering. It lets us use mathematics to understand a design space, optimize towards a better solution, and sometimes unlock things that looked impossible from the original representation. What makes modern AI strange is that language is now part of this pattern. And I mean more than language. Text, code, images, audio, diagrams, sensor readings, constraints, tasks, maybe even eventually many kinds of physical state. Anything that can be represented in a form the model can transform. Not perfectly, not magically, but practically. A sentence can be broken down into tokens. Those tokens can be turned into vectors. Those vectors can move through a learned high-dimensional space where relationships between words, concepts, code, images, and tasks become computational objects. Then the system can transform that internal representation back out as English, Python, an image, a plan, a shell command, a structured data record, or some other compatible representation. That is the part I think it is easy to understate. We did not just build better autocomplete. Yes, prediction is part of how these systems work. But the deeper thing is that we built machines that can move human representations into a space where computation can act on meaning-like relationships. I'm not claiming the model understands the way a human understands. I am claiming that the transform preserves enough relationship structure to be useful, and that is already changing how people work. The smallest visual example is the classic word vector analogy. King minus man plus woman gets you something close to queen. That example is overused, and it's not even close to how every concept works, but it still shows the shape of the thing. In vector space, words can become locations, relationships can become directions, similarity can become distance, search can become geometry. If you search for something like big cat with a mane, a vector search system can find lion, even if the word lion never appeared in the query, because the concepts land near each other in the learned space. Before this transform, words were mostly symbols on a page. Now they can be points, neighborhoods, directions, and transformations. That opens a new domain for computation. The practical example most programmers already feel is code. You write something like, build a small API endpoint that takes a user ID, checks whether the user has an active subscription, and returns the current usage limit. That is not code. That is not even a full specification. It's the kind of thing a product manager might say to an engineer. There are a lot of details missing. What framework are we using? What does the database schema look like? What does active mean? How should errors be handled? What happens if the user does not exist? But it is intent, written in compressed human English. A model can transform that intent into Python, TypeScript, SQL, tests, or documentation. In a text-only model, that is still text to text. But the useful mental model is that the word Python is operating on the rest of the intent in representation space. It moves the request toward the Python-shaped region of that intent. Then the model transforms it back out. You get code, not because the model is thinking like a human. It is relational. It is transformative. It is transforming something non-specific into something specific enough to run on a machine. And that is exactly where the danger lives. Because the input is missing information, the output has to contain assumptions. Sometimes those assumptions are helpful. Sometimes they are wrong. Sometimes they are inevitable. Sometimes they are invisible until much later. This is why coding with LLMs can feel both incredibly powerful and strangely slippery. The transform preserves some things, invents some things, and loses others. Once you see the pattern, text-to-image stops feeling like a separate miracle. The useful picture is not just text goes in and image comes out. The useful picture is text encoder, shared representation space, image decoder. The front half transforms language into a representation. The back half transforms a compatible representation into pixels. If the spaces are aligned well enough, you can cut across modalities. Text can become an image can become a caption. A camera view can become a robot action. A sketch can become an interface. The boundaries between text models, image models, audio models, code models, and agent systems start to blur because they are all learning ways to move between representations. That does not mean every transform is equally good, and the question changes. The question becomes what kinds of representation can be transformed into what other kinds of representation, and how much useful structure survives the trip. Every powerful transform has assumptions. Fourier analysis can make frequency structures visible, but it emphasizes some things and hides others. Laplace domain control design can make dynamic systems easier to reason about, but initial conditions, nonlinearities, and modeling assumptions still matter. JPEG compression keeps the parts of the image that usually matter to human perception and throws away detail your eye may not notice immediately. The fact that a transform is lossy or assumption dependent does not make it useless. Often, that is exactly what makes it useful. But it means you have to know what kind of loss you are accepting. With LLMs, I think the loss is often semantic. Not always factual loss in the simple sense, not always a hallucination. Sometimes the model preserves the broad intent while losing a constraint. Sometimes it keeps the shape of a request while changing the edge cases. Sometimes it fills in missing information with reasonable assumption, and that assumption becomes part of the output even though no one explicitly chose it. In the API example, active subscription might become a Boolean field, a join across billing tables, a call to Stripe, or a cached entitlement. The model has to choose some version. That choice is where loss and invention enter the output. For this project, I have been calling that semantic transform loss. The exact term matters less than the mental model. When we transform human intent through a learned representation space, the result can be useful without being a perfect preservation of the original. Missing content can become executable assumptions. So the big claim is not that LLMs are magic. They are definitely not magic. It is math, it is computation, it is training, it is data. The claim is also not that vector space literally contains human meaning in some mystical way. The useful claim is simpler. We have found a practical way to transform language, code, images, and other human representations into a space where we can apply computation, extract relationships, and transform the result back out. This mostly used to happen inside human interpretation, inside human brains, inside human organizations. That's why the impact feels broad. Not because chatbots are one product category, because the underlying pattern touches almost every kind of symbolic work. Writing, programming, design, research, planning, review, coordination, education. Any workflow where humans pass around a representation of intent is now at least partly exposed to this new transform layer. And if history is a guide, when a new transform makes a space computable, the first applications are not the full story. The full story is the technology tree that grows after people learn how to think in that space. Thinking in the limit is a thought exercise I like to use. You find the trends in a new technology, you project those trends outward, you ask what changes as they approach zero, infinity, or whatever practical asymptote they seem to be moving towards. So let's push this trend. Accuracy keeps going up. The complexity of what these systems can handle keeps going up, and the cost of generating another artifact keeps going down. Another paragraph, another image, another program, another test suite, another design, another experiment plan. When you push those trends far enough, the bottleneck changes. The important question is not just what can the model generate. The important question becomes what can we validate, what can we verify, what can we trust enough to connect back into the world. There is a useful distinction from safety-critical engineering. Validation asks whether we built the right thing. Verification asks whether we built the thing right. Both matter, but for this transform, validation may be the deeper problem. Because a model can build something coherent, polished, and locally correct while still missing the real goal. It can satisfy the prompt and fail the purpose. It can preserve the shape of the request and lose the reason behind it. Right now, generating code is already getting cheap. Generating text is cheap, generating plausible designs, test cases, plans, and documentation is getting cheaper. But knowing whether they are the right artifacts is not cheap. In the limit, plausible output becomes abundant. We are already dealing with it in this software engineering. Trustworthy output that still fits its purpose becomes scarce. This is because software starts to look more like safety-critical software, even when the software is not flying an airplane. You need requirements, you need tests, you need traces, you need reviews. You need evidence that the thing you built still connects back to the thing you meant to build. When generation is expensive, the artifact is the work. When generation becomes cheap, the work moves to proving that the artifact is the right one, and that it behaves the way the world needs it to behave. That is not the glamorous branch of the technology tree, but it may be the load-bearing one. Now take the same trends and push them further. Accuracy up, complexity up, generation cost down. The normal version is that a model writes Python. The far-out version is that a model transforms intent, runtime state, constraints, and performance feedback into a low-level executable representation, something near the boundary where software becomes hardware behavior. Not necessarily literal machine code, something more like a PTX-like intermediate execution layer, or another representation that can be compiled onto the machine. That distinction matters. Runtime code generation already exists. JIT compilers already exist. Self-modifying code already exists. So the novel idea is not code appears while the program is running. The novel idea is a learned transform loop. The system has a representation of what it is doing, what it is trying to optimize, what it is trying to achieve, what constraints it cannot violate, and what just happened. It transforms that state into executable behavior. The hardware runs it, the system measures what happened, that measurement feeds back into the next transform. At that point, the software is no longer just an artifact the machine runs. Software becomes part of the machine's own feedback loop. The computer starts to inhabit its own execution. That is the weird limit, and it is also where validation and verification stop becoming optional. Because if the system can continuously generate new executable behavior, then the safety boundary cannot be a human reading every line. That boundary has to be intrinsic validators, constrained execution environments, proofs, tests, monitors, traces, and evidence. And probably new ways of validating and verifying generated software that we have not invented yet. Source code does not necessarily disappear. It may become more important as an audit surface, but it stops being the only imaginable bridge between intent and execution. Once you see that loop inside the machine, the same shape appears outside the machine. A hypothesis becomes an experiment. The experiment becomes a simulation, a lab procedure, a robot protocol, or a piece of code. The result becomes measurement. The measurement becomes evidence. The evidence becomes the next hypothesis. Autonomous labs and automated discovery systems already point in this direction. But the limit thought is not just AI does science. That's too generic. And automated discovery systems are already starting to push beyond what humans can easily reason through manually. The limit is that representation transforms compress the loop from question to action to evidence and back. The system does not merely answer a question. It proposes the next thing to try. It generates the procedure. It runs or simulates the procedure. It measures what happened. It updates the representation. Then the loop runs again. In the inward version, the system is transforming runtime state into executable behavior. In the outward version, the system is transforming intent into experiments and experiments into evidence. Those are two faces of the same deeper pattern: representation, action, measurement, updated representation. That is where the technology tree gets strange, not because the model has a perfect mind, because a cheap, accurate enough transform loop can search through possibilities faster than a human organization can manually translate every step. This also changes how I look at ordinary workplaces. A company is mostly just a series of transform pipelines. Someone has an intent, that intent becomes a strategy deck. The deck becomes a product brief. The brief becomes a design. The design becomes tickets. The tickets become code. The code becomes a product. Every handoff is an intermediate representation, and every handoff changes the thing. Not always by accident, often on purpose. Each representation is shaped for the next audience. The customer should not have to read code. The executive should not have to read every ticket. The compiler should not have to understand a strategy deck. Human professionals add value because they transform the idea for the next stage while carrying context, judgment, and constraints. But when representation transforms get automated, some handoffs compress. Smaller team can express intent at a higher level and get more executable structure back. A founder can move from idea to prototype through fewer translation steps. A researcher can move from hypothesis to experiment design to analysis faster. That does not mean organizations vanish. That means their shape changes. The goal moves towards choosing the right intent, setting the right constraints, validating the goal, and verifying the outputs. I do not think the right question is simply, what can AI automate? That question is too small. The better question is, what new transformations between human representations are becoming possible? What information survives those transformations? What gets compressed away? What assumptions get added? And what new tools, institutions, and workflows become possible when we learn to engineer around those trade-offs? That, to me, is the interesting thing. Language is becoming a computable material, not perfectly, not safely by default, not without loss, but enough to matter. And when civilization gets a new transform space, the technology tree changes.